This video introduces deep belief networks. Deep belief network is a generative model consisting of one undirected, restricted Boltzmann machine on the top of the model, followed by a sequence of directed graphs, which convert the representations in the hidden units into new samples, such as the pixels of our image. It's a difficulty by directly training the entire model to infer the conditional distribution of hidden variables H given a data vector V. A greedy layer-by-layer pre-training method is used to train the model. Likelihood is defined as a margin of joint probability of V and H over H. Using chain rule, we express the likelihood as a margin of product of probability of H and the conditional probability of V conditioned on H over H, where Z is a partition function. The probability of a unit I in the first hidden layer being on is computed independently from the units J in the visible layer through this sigmoid function. When hidden units are used to generate new samples, the dependent probability prior is equal to product of independent probability of HI, will cause a phenomenon of explaining away. Namely, probability of HI increase may lead to probability of HJ decrease. Our extra hidden layer is used to eliminate explaining away through a complementary prior. Greedy method provides the initial value to the actual hidden layer from training data through the tight weight WT. Namely, we first train the first block, give the training data to the initial value. And then we train the second block. His initial value is generated by the learned W from training data. And so on until we reach the end of the model. That is the restricted Boltzmann machine used as a terminator. If the prior from actual hidden layer matches with the likelihood, the explaining away will be disappear. For a deep belief network, the top graph is undirected RBM, and the downward graphs construct a generative model. And the upward arrows provide initial values to train the deep hidden layers here. The upward computations are not part of the model. Gibbs sampling is used to compute the gradient of likelihood with respect to model parameters. The gradient of the likelihood is computed by the difference of two expectations over the data distribution and the model distribution. Namely, first we give the training data as the initial value to the first block. At a time t, we update the value H0 in the first hidden layer. And then now we calculate the expectation over the data distribution. And then at t equal 1, we update H and V, we get Markov chain until reach the Slytherin distribution. And then we calculate the expectation over the model distribution. We only calculate the expectation in the first block because all the contribution from deeper hidden layers is combined to the first hidden layer. For more details, please check with these references. Thank you. Bye.